Okay, so we have a hopefully much shorter and simpler assignment this week that is due on Wednesday. I tried to keep it 100% relevant to the 8th. And short enough that you weren't trying to prioritize too much this class over the 8th. Because this is a big week. Does anyone have any questions or concerns about the upcoming schedule, about the 8th?
Are you gonna have a homework due this following week, maybe next week, or how are you gonna face that?
Something next week. I don't know exactly when. It'll depend on the size of the assignment when I write it. I'm anticipating it's probably going to have 3 elements, which would be implementing a linked list stack, implementing a postfix evaluator, and then implementing an infix to postfix converter. We'll go over both of those things today. So that seems like it would be an assignment that's a bit on the larger side. I want to give people a little bit of recovery time from the 8th, so maybe this becomes something that's due next Friday rather than next Wednesday, but I'll make that final decision eventually.
Okay. You know, you might post that thing.
We definitely have to go over the material, which should happen today, I think. I'm known to not quite get as far as I think I will, but it should be posted over the next couple of days. I have to make sure I go write it as well. I also plan to release a study guide for the next exam, which will be a week from Friday, on Friday.
Week from this Friday?
Yeah. We're already on week 5 somehow, which means that end of week 6 is the second exam, and we started to go over quite a bit. So it's probably time to make sure that the exams don't cover too much material. I've definitely had both issues where the main issue is that there's just too much content on an exam. That's never good. All right, so we're going to start today off by implementing the stack. I had you doing this in groups, but let's quickly just go implement it and talk about it. So the first thing we needed here were the fields of the stack. So what did we need to store to make the stack work? We really only need the underlying list and a size, that is the number of elements. We need to know where to go find the top element of the stack, but the size is going to do that for us. Size -1 is always where the top element of the stack is going to be. So let's actually go do that. We're going to have 2 fields, an array list. So the question is, should we try to code this generically, or should we try to code this with just integers? Let's try to do it generically. I call this elements. Then we're going to have an int size. And as usual, when you're making a new object, you do not want to initialize these fields. You want to let the constructor initialize these fields. So they're going to have their default values in the meantime. We can't have this structure, it's way too small. We can't have this structure without a constructor. So trying to set these values just doesn't make sense. Unless they were static. If they were static, then you could set them without a constructor. So a constructor. Does the stack need any parameters in order to be constructed? I agree. I don't think so. So let's go ahead and set our fields. We can say elements equals new array list T. We don't know enough to put anything in there yet. Stack should be stack array list. There we go. And the initial size is 0. When we make a new list, there aren't any elements in it. Seems like a reasonable constructor. We've set the values of our fields, which is the entire purpose of our constructor. So now we're good to start implementing. So let's go back to our stack methods. The first thing we want to implement is the ability to add something to our stack. So we're going to write a push that takes in an element of type T. We want to add that to the top of the stack. It should be the rightmost element because we need all of these to be in constant time. And if the top is the first element, then whenever we add or remove, let's say we're going to add, we have to move everything to make space for it, which is no longer constant time. Whereas if we make it the end of the list, then we can access that and add and remove to it in constant time. So the only way for a stack to work is if it is the end of the list. Now note that if you have a linked list version, it doesn't matter. Because you can just modify the head and the head's connectors, or the tail and the tail's connectors, just as easily as each other. As long as you have both a head and a tail pointer. Some linked list implementations don't store the tail. If you don't store the tail, then you have to go find the tail, which is not going to be a constant time operation. So how do we implement push? The goal is to add it to the top of the stack.
You just use the add function.
Yeah, exactly. We can say elements dot add element. Is that it?
The add adjust the size.
This add does not have any idea that this size exists. It adjusts the size of elements. So if we wanted this size to somehow be elements dot size, we would need some way of keeping track of that in real time. Even if we said size equals elements dot size is 0. And this will not continuously update as elements dot size updates. So we need to do something in our push that is going to change our size. Anything else need to be done? I think the answer is no. It's pretty straightforward when you have the underlying list. Remember that I said that really we're just using the lists built-in tools to do this for us. So we don't really have to do too much logic. But if we wanted to make one of these stack array list objects, we'd be able to use this object where everything would be in constant time. The issue is that we're only going to have access to that last element in the list. So that's push. Back to our slides. Next one is pop. It's going to return something of type T. We want to remove the top element of the stack and return it. Now, we're going to run into one issue here. Should we be able to pop if the stack is empty? No. So this is going to throw an exception. We just want to check if, and we're going to write, and in fact, we can really quickly write is empty. You could just add the if size is equal to 0 here, but it's typical to have something like an is empty. And this also increases the readability of your code. So if this stack is empty is much better than if size equals 0, because what does that mean? It may be apparent to you in this case what that means, but just having some name for it here really helps the code readability. So if the stack is empty, what kind of exception makes sense here? A legal argument would be for if there was some kind of parameter and the parameter was wrong.
Index 7.
I'm gonna go with illegal, illegal state. Trying to pop from it creates an illegal state. Import. Yep. Once we get past this, we know that the size is at least 1, which means that we can pop. So we want to. First, since we want to return it and get rid of it, we want to bump down the size. Do we want to remove it from the list?
And what index you use.
So anything that's outside of this size is not technically part of our stack. So we don't actually need to do something like list.remove. We can keep it there. We can keep the old thing there. But if we try to go add, then the list elements is going to think that it's part of it. So that would be really bad. We'll be adding at the end of that and not what we want. So that would give us some kind of, so we do actually want to remove it. We want to remove it at an index. What index do we want to remove at? Size -1. And we've successfully removed something, so we should decrement the size.
What we want to return.
And then we want to, yeah, I guess we need to store it, don't we? We need a. That should do it. We agree? We're going to store off the element that's at the top of the stack. Then we're going to remove it from the underlying list. Decrement the size of our stack and return the element that used to be at the top of the stack. Between all of that, then we have succeeded at the pop. We've removed it and returned it. Do any of these operations take more than constant time? Some of these can. For an array list, get never does, but remove can. Remove can take linear time. But if we're always accessing that size -1 index, then that is the end of the array list. There's no moving that needs to happen. All right, that is pop. Peek is exactly the same thing without the remove. Now it's not really an illegal state. It's more like a, you just can't do this right now. So rather than throwing an exception for this, I think we just return null. Because T, we don't know what type that is, but we can always return null. So if is empty. Turn null, there was nothing there. Now we want to just straight up return elements.get, since we don't need to remember it. Because we're going to remove it and decrement the size, we can just go straight to the return statement. Return elements.get of size -1. And we've taken our 3 lines here, 4 lines, and reduced that down to 1. Much simpler. Questions about any of these implementations so far? Next one is we just have size and is empty. We've already done is empty, so we just need a size method. And this is because all of these should be private. So we should not allow outside access to this size. We want it to be read only. So because of this, we need some way for the user to know how big the size is. So we'll just return size. This is basically a getter for the size. It allows public real-time access to the size of this stack. Sweet. So I think we can test this out and see if we can manipulate a stack. So let's do that. Let's make a quick driver class that uses this. I don't want to put this in the same class because it's not necessarily related to the structure of the object. So we're just going to make a new driver class. We'll call this stack array list driver. We're going to write a main. Inside of that main, we're going to make a stack array list object. Stack array list. We'll run this with integers because that is the easiest thing to test. We'll call this list, the stack. If you capitalize it, then Java thinks that it's some kind of built-in stack object. So keeping them lowercase is good. All right, so what do we want to do to our stack to test it out? What makes sense to do? Push to it. So we could stack dot push, and it takes an integer. What do we want to push to the stack? 13. Always a good choice. What do we want to do next? Let's quickly check the size of our list and make sure that it is. Then we could pop. Now, know that this does return the value that was popped. So one thing we could do is set that. So we could print that out. If we print out something like the value on top of the stack was then we get that value back for us. It is perfectly fine if you do a stack.pop and don't store the value if you don't care about it. If you want to pop off the stack and you don't care about the return of 13, then that's perfectly fine. But be careful, if you care about what was on top of the stack, you need to store it. So after we do that, we could check the size. Or try to pop again and make sure that we get our exception. Which of those do we want to do? We want to push a few things? Do we want to check and make sure things work? Check and make sure they work. So just doing it would force an exception, which would crash our program. But we can do something about it if we, for instance, just wanted to check that. If we just wanted to check it, then we do it in a try catch. So we're going to try to stack dot pop. We will catch, and usually the catch goes on the same line. We called it an illegal state exception. What's something clever we could do about catching If anyone knows the reference, I will be very happy. Does anyone know the reference? No Path of Exile players in here? We'll have to change that. There's an NPC who follows you around, and the goal is to reduce Beast's health down to a critical value. It says, "You have been captured, stupid beast." Excellent. So we can try and catch that, which will fail to crash our program, which is good, so that we can reach something after the try catch that says something like, "We made it to the end." Great. So we can run this. I hate my life. Does it work? People got it? So this JRE system library seems like every time I launch this, I have to re-import the JRE system library in order to be able to run anything from this, but it looks like everything is working. We made it all the way to the end. So this is how, in the middle of a driver program, you can check for an exception. Just do a try catch, catch the appropriate exception, and then inside of the catch, you can do whatever you want with that exception.
Why do you put E in there?
This is the name of the variable. So basically, you can now use this to do something with the exception. Usually what's done by default when you see the red text is you get for free A or E dot print stack trace. This just shows you everything that was on the stack, which method calls were there before you got that exception. So then that allows you to debug that. You can also do logic associated with basically, if this exception is of a particular type, then do this. If an exception is of another particular type, do that. And it allows you the full creative control of the Java programming language to try to recover from that exception. This is why we don't put the error handling logic inside of our tools that we write. So our stack should not try to handle that exception. We don't know why the user was trying to pop from an empty stack. So we just throw the exception and we let them handle it. And now that we're playing the role of the user in our driver class here, now we can say, what do we want to do about it when we get it for whatever it is that we're trying to do? We don't want to assume that as the tool writer. This is why it's also important to add those things in our Java doc comments, like our throws. This tells the user, if they look up the API for pop, if you try to pop from an empty stack, then you will receive an illegal state exception. So by reading this, we can now write the associated code that deals with it. So the API is really just clarity to the end user that says, here is how you use my tool. Questions about stacks, implementing stacks, using stacks? The array list is kind of the slightly easier implementation of a stack. As part of your next assignment, you will be implementing these methods with your linked list. It should be fairly straightforward to do with a linked list. You shouldn't need to do anything too crazy, but you will need to be at least mentally aware of how the connections are updating as you do things like add at the end, remove at the end. But if your linked list code is already working to add at the end and remove at the end, you will find no issues. If you try to write the stack and test the stack and you find that there are issues, maybe there were some issues with your linked list with regards to adding or removing at the end of it. All right, I'll keep this around, upload it to Canvas. And we have a few minutes, half the class, to continue. All right, so we discussed how every method on the last slide needs to be constant time. The reason behind this is that stacks are consistent constant time structures. They give us as much functionality from a list as we can possibly get with guarantees of constant time for everything. And it turns out there are lots of problems that we can solve with just a stack. It's not appropriate for every single problem that we could use a list for. But every single operation being big O of 1, regardless of the size of the stack, is very powerful. And it allows us to do some pretty cool stuff. Can anyone think of ways that a stack is used? Where would this functionality be seen in real life? Where have you used some tool where the implementation would make a lot of sense to be a stack? How about something like undo, redo? Whenever you make a change to something, push it onto the stack. Whenever you want to undo some sequence of those things, it has a history of what you have done. So it just undoes the last thing you did and the thing before that and the thing before that. You don't want to undo something 4 or 5 times ago. Those are embedded way too deep in the stack. You only ever want to undo the last thing that you did. Once you undo, you would like to be able to redo. So it turns out that undo redo actually uses 2 stacks. You have an undo stack and a redo stack. whenever you undo something, rather than forgetting about it, you push it onto the redo stack. And then the last thing that you undid becomes the first thing that you redo if you want to redo something that you previously undid. So it's a two-stack system. Very similar to something like the browser history of back and forward. If you push the back button, then you're going to recall the last site you were at. So we store a history of sites in a particular session that you visited, so that if you click the back button, we remember that and go back to it. There are plenty of others, we'll talk to them, but those are the ones that I think everyday use for the generic population. You see stacks for that. One fun application is, we're gonna call this postfix notation. Let's get some intro on it. When we write a mathematical expression, we use parentheses in order to override our standard order of operations, because we don't have enough information in our standard order of operations to be able to write any particular expression. So we want to be able to have full control over our orders of operation. Is there any way that you can think of to express some kind of mathematical expression where the goal is outside of the standard order of operations? So for instance, we want to do a quantity 5 plus 3 times 2. What do you have to do to this to write it in a way that has no parentheses?
Like left to right. On each operation.
So we want no parentheses to be here whatsoever. We actually have to modify its form. We have to flip the order of these things, so we need the 2 times to come first. 2 times, but we still need to resolve this, right? If we do 2 times 5 plus 3, we can't get rid of the parentheses. There's just no way to do it. We need those parentheses to override the order of operations. We need to evaluate this before we can do the rest of it, which is really annoying from a computer's perspective, because how do we think a computer does this? How does a computer resolve this? We know computers are really good at addition and multiplication, but how does it identify which sub-expressions to calculate first?
It adds the first parenthesis to the stack, and then it like does one operation until it gets the next one.
Yeah, so it needs the parentheses, right? There's more going on there than meets the eye. It turns out that parentheses aren't needed. But in order to remove parentheses, we need to figure out a new way to evaluate expressions. We cannot use the type of expression that we are used to. So what I've been writing and what you are used to is called infix notation. In meaning inside of the expression, we can have, we have our math symbols, our operators. So the plus, the minus, and the times, and the divides, and the exponentiation. So if we have something like a plus, we have sub-expression 1 plus sub-expression 2. And then the plus says add whatever the result of sub-expression 1 is with the result of sub-expression 2. If we want to evaluate some of the things within sub-expression 1 or sub-expression 2, before we do this, this makes much more sense if it's something like a times. If we want to do any of the addition and subtraction first inside of these sub-expressions, we need parentheses to override the order of operations, because otherwise we're going to be doing this with parts of this. So we need to grab the entirety of sub-expression 1 and sub-expression 2 with parentheses if we don't just want to multiply it with parts of them. So this is called infix, where the operator is in the expression. In the middle of the expression. Now we have a really weird looking face. A really scary face. I'm gonna get rid of it. So sub-expressions look like this. If we're a computer, we have to do something with the parentheses because, or there have to be parentheses, and we have to use a stack to identify where a parentheses starts and ends, because otherwise there's no way to calculate anything. So we have to resolve the sub-expressions A and B before we apply the operator. Which means that we're going to be parsing throughout the entire expression rather than just from left to right. It would be ideal if we just had a way to read a symbol, read a symbol, read a symbol, read a symbol, operate. And not have to scan the entire expression for parentheses and figure out what to do with those parentheses and then backtrack. It seems like that's a lot more work than necessary. So we're going to learn a new kind of expression notation called postfix, and it will allow us to evaluate an expression from left to right with no backtracking whatsoever. And honestly, this is the way we should be teaching everyone from the very beginning. This should be the standard way that expressions are written, in my opinion. So now, instead of the operator coming in the middle of the expression, it is going to come at the end of the expression. We're going to see all of the numbers, and then we're going to see what we want to do with them. So here's an example. 8 6 plus 10 times. What this tells us is we can use a stack for this. We're going to, when we see a number, push it. When we see an operator, we're going to pop to, apply the operator, and then push the result. So we start with a number, 8. We just push it on the stack. We then see another number, a 6. We're going to push it on the stack. We then see a plus that tells us, take the two things off the top of the stack and apply the plus operator to them. So we're going to pop a 6, we're going to pop an 8, and we are going to apply the plus to them. I'm just drawing this in infix notation so that this is what we are used to. This is saying do the 6 plus 8 operation. Result is 14. We push that back to the stack. We then push a 10. But there are again two things on the stack such that when we see the times, we're saying pop these two elements off the stack. Note that we don't need to think about what happened first anymore, and apply the operation. So we pop the 10, and actually I should be drawing this as second. So now we have a 14 times 10. We are going to evaluate. We are going to push the result back on the stack. And by the time we are done with all of these operations, what we're left with is the answer on top of the stack. Did we override the standard order of operations as we did this? So if we were to write this out in infix, this was 8 plus 6 times 10. Because it was written like this, we had parentheses around this because we did the addition first. And no parentheses appeared anywhere in this expression. And in fact, you have complete control over the order of operations just in the order these symbols appear. There is no standard order of operations in postfix. Whatever appears first is done first. No ambiguity. You never have to go back when you're evaluating a postfix expression. You never need to refer to a previous number or to a previous operation. You just need to parse from left to right with the two simple rules of when you see a number, push it to the stack. When you see an operator, pop, pop, evaluate, push. It is so clean, I can't believe we don't do it by default. It's the same thing as just getting over our independence from Britain and using the metric system. Just get over it. It's been hundreds of years. It's way better. Deal. All right, so I want to do some postfix examples. So go ahead and try to solve the following. 2, 3, 4 plus times. Attempt to do this in your head, or you can draw it out with a stack and see what happens as you go through the logic of when you see a number, push it. When you see an operator, pop twice, push the result. Yeah.
We always pop twice. When we see an operator.
Yes, because plus takes two things. You can't just like 8 plus doesn't mean anything. Plus 8 doesn't mean anything. So we need a left-hand side and a right-hand side. That means that there are possibly invalid postfix expressions. I don't have any of those here. They should all be valid. What do we get? 14, that is correct. How do we get 14?
Pop 3 and 4 and you add them, put it back on the stack. You pop 2 and 7.
Yeah, so this plus is going to refer to the two most previous elements. The 3 and the 4. 3 plus 4 is 7. Now we have 2 7 times. So we're going to take the equivalent of 2 times 7, which gives us 14. If we're doing this in a stack, and just kind of drawing out the history, we have 2, we push 2 and 3 and 4. Honestly, I'll just draw this out in terms of the exact order that we do them. When we see the plus, we're going to pop twice, evaluate, and push. So popping twice has us doing 4 plus 3. So now we see 2, 7, and then we see the times. So we see doing the equivalent here of 2 times 7, we get 14 is the only thing that is on the stack. So at the very end, we just either peek or pop at this value and see that the answer is 14.
Can you do another example?
Yeah, we have I think 3 more at least. Questions about this example? All right, here's the next one. 2 4 times 3 5 times plus. Yeah,
23.
23, that's what I get too. Looks like we have some consensus. Let's actually draw it out as some stacks and see what's happening. So we see a 2, push a 2. We see a 4, push a 4. We see a times, so we are going to do the equivalent of 2 times 4, which evaluates to 8. We push that back on the stack. We now need to push a 3, push a 5. You're now going to pop twice and evaluate for the times that we see. So we're doing a 5 times 3. Note that this is great for operations that have commutativity, like addition and multiplication. When we get to division, we need to make sure that we're doing this correctly. So there's an obvious right way to do this if we are doing this. So we want the first thing divided by the second thing. So this should actually be 3 times 5. I'm going to make sure I write these in the right order, even though they're commutative, because you take the second thing as the first thing, and the second thing you pop becomes the first thing you evaluate, because it came first in the expression. So 3 times 5 is 15. So finally, we see a plus operation. So we're going to take 8 plus 15, push 23, and the result of this expression is 23. Questions on this example? Why weren't we taught this from the beginning? We don't need order of operations. We don't need parentheses. Those were all useless things that you were taught that you will never need again, right? No, we need it to interact with the rest of the world. Things we discover as computer scientists that make us alone and afraid inside. 2, 3 minus 4 plus 5, 6, 7 times plus times. It's a little bit harder to do in your head as you go. Disagreement. I love to see it. What'd you get?
141.
141.
Oh.
3 different answers.
That's really nice.
So since we are basically out of time, I don't quite have time to draw all of this out as stacks today, but we're going to start with that tomorrow. My recommendation for people between today and tomorrow, solve this expression. And eventually what you're going to be doing with this is you're going to be making a postfix evaluator that will allow the user to type in an expression like this and you'll solve it. And then the second and much harder problem is given an infix expression, convert it into the equivalent postfix. So you can start thinking about how to do that. And tomorrow in groups, we're going to be devising the algorithm for how we're going to be converting infix to postfix. How could we do that? I'll see you tomorrow for that.
I guess it's 2 minus. Oh. That's
Yeah, so the fraction is not commutative.
Not
Yeah, I thought negative one.
Yeah.
That big of a average.
Does.
Yeah. I like to grade my answer.